Good evening all. Welcome to the phase 2 week 1 of GATE session. My name is Veena. I am pursuing PhD from IIT Madras. Today we will be discussing 4 questions, 2 from networks and 2 from machines. So let's start. I hope everyone's ready.
Yes, ma'am.
So the first question is, the Thevenin equivalent voltage VTH in volts rounded off to 2 decimal places of the network shown below is. So this is a networks problem, which is very simple. So whenever such problems are asked, it is better to redraw the circuit in your paper. And first step is you have to assume a ground potential to one terminal. Now Thevenin equivalent voltage across any terminal is, you have to open that terminal and you have to find the voltage across that terminal. So these 2 terminals, say A and B, they are open. So there is no current flowing through this branch. So if this B terminal is grounded, the potential at A is VTH. So since the drop across 3 ohm is 0, the same VTH will apply across this terminal. Now we know that 5 ampere is flowing. Nothing flows through this branch because it is open circuited. So the whole 5 ampere will flow through 2 ohms. Am I right? Can someone respond?
Yes, ma'am.
So 5 ampere, you know that current always flows from high potential to low potential. So VTH is higher potential, that's why current is flowing in this direction. There will be a drop of 5 times to 10 volts across 2 ohm. So potential at this point is VTH. A 10 volt is dropped across 2 ohm. So the potential at this point is VTH minus 10. Now you observe that the potential at this point is same as 4 volts because this is ground potential. Potential at this point is 4. So VTH minus 10 is 4 or VTH is 14 volts is the answer. Is it clear?
Yes, ma'am.
So most of the problems you can solve just by analyzing the circuit rather than directly writing KCL or KVL. Moving on to next question. The voltage across and the current through a load are expressed as follows. Voltage V of t and current I of t is given. The average power in watts round off to 1 decimal place consumed by the load is. So we are given a load. The voltage across the load is V of t is given and current through it is given. Average power exists only between similar frequency components. Say you have V of t, it has frequency components F1, F2, so on. And you have I of t. If I of t also has F1, F2 or till F3 only, but this has say F4, average power will be formed by F1 components, F2 components and F3 components. So consider a case when V of t, or in this problem, we have V of t is having a component of frequency 377. I of t also has a component 377. So in this case, there exists a active power because both voltage and current are having same frequency. Suppose in the question, this was 375. Then what would have been the answer? Can someone tell me? If the question was V of t minus 170 sine 375 t minus pi by 2 and I of t same as in given, what would have been the answer?
Ma'am, both are different frequency components, so no active power.
Correct. So for different frequency components, active power will not be there. So hope that point is clear. Now we can proceed with this question. So when 2 waveforms of similar frequencies, we have voltage and current. Say V of t is Vm sine omega t plus one angle say phi 1 and I of t is Im sine same frequency omega t plus or minus phi 2. Then the active power is given by V max into I max by 2 cosine of angle between them. In this case, since both are sine, the angle will be phi 1 minus phi 2 or phi 2 minus phi 1. Because it is cos, it doesn't matter. Cosine of theta is same as cosine of minus theta. But in the question, one component is minus sine and the other component is cos. So when such questions comes, we can approach it in a quadrant form, where I assume a quadrant where my x-axis is sine omega t. We know that sine wave looks like this. If this is omega t, sine omega t looks like this. Now cos omega t will be like this. Hope everyone is clear about this.
Yes, ma'am.
So that means cosine wave leads sine wave by 90 degree. Cos comes first. The peak of cos comes first, then sine. So in this quadrant, where will my cos omega t comes? If I am considering a rotation in this direction, where will cosine wave comes?
Y-axis.
Correct. So this is cos omega t. I am moving in this direction. So in such condition, cosine is leading sine. This is the representation. So if this is the case, this axis will be minus cos omega t and minus x-axis will be minus sine omega t. Is it clear? Does anyone else know this approach?
No, ma'am.
Okay. So this way we can construct a quadrant of sine and cos. Now in this quadrant we have to locate the vectors v and I. We can locate vectors provided they are of the same frequency. So now we have v of t, v vector whose magnitude is 170 and angle we don't know the position. So before that I'll tell you one more point. Consider cos omega t. You know that it will look like this. What will cos omega t minus 30 degree looks like? You substitute omega t is 0. That is at this point. When omega t is 0, cos minus 30 is same as cos 30, which is 0.866. So that will come here. Now put omega t as 30 degree. At 30 degree, cos 30 minus 30 will be cos 0. Cos 0 is 1. So at 30 degree, your cos omega t minus 30 is 1. Similarly, put omega t as 120 degree. So 120 will be around here. At 120 degree, cos omega t minus 30 is cos 120 minus 30, which is cos 90, which is 0. So cos omega t minus 30 will become 0 at 120 degree. Now what is the phase difference between these two waveforms? To find phase difference, you consider any two similar points. So here let us take this point where the waveform reaches 0. So for cos omega t, the waveform reaches 0 at 90 degree. For cos omega t minus 30, the waveform reaches 0 at 120 degree. So the phase difference between these two angles is 30 degree. Also another point we note is that cos omega t minus 30 will lag cos omega t by 30 degree. So when you generalize, you can write cosine or sine cos omega t minus theta will lag cos omega t by theta. Similarly, cos omega t plus theta will lead cos omega t by theta. Is this point clear?
Yes, ma'am.
Okay. So we come back to our problem. First is v of t. V of t is 170 minus sine 377 t minus pi by 6. Pi by 6 is 30 degree. So minus sine omega t is this axis. Now v of t will lag minus sine omega t by 30 degree. Is it correct? Does it lead or lag?
It's lagging.
It's lagging because the sign is minus. So lagging will come here or here. This is A, this is B. It will come in which quadrant? In the given rotation, you know that when it comes before it,
A.
correct. So when it is lagging, it will come behind minus sin omega t. So minus sin omega t is here. So V of t will lag minus sin omega t by 30 degree. So your V vector will come here. Now let us write where I vector comes. I vector is base is cos omega t. So this is the base plus pi by 6 or plus 30 degree. So it will lead cos omega t by 30 degree using this logic. So your I vector will come here. Is this clear?
Yes, ma'am.
So I vector will lead cos omega t by 30 degree. So now you got V vector and I vector and you know their positions. So what is the angle between V and I?
30.
30 degree, correct. So the answer is 170 multiplied by 8 by 2. Cosine of angle between them is 30 degree. This is how you solve this problem. You can try with another example also. You can take plus say 8 minus cos omega t plus 60 minus 4 sin omega t plus 30. This is not 377. This is something else. This is say 374 and this is 374. So in this case, you draw another axis because each quadrant is for a particular frequency. So let us try solving this also. So here it is sin omega t. This is cos. This is minus sin and this is minus cos. So this is minus 8 cos 374 t plus 60. So someone tell me where it will come.
I didn't get what you asked.
Okay, I have added one more frequency component in my voltage. It is minus 8 cos omega t plus 60. And I of t I added minus 4 sin omega t plus 30. I have quadrants 1, 2, 3 and 4. Where will my voltage vector comes?
It will lead. It will come second quadrant only.
It will lead what? I have
Current
sin, cos, minus sin and minus cos.
second quadrant it shall come because it's cos.
I'm leading cos.
It is minus 8. Minus 8 cos. So you have to consider 8 times minus cos. So you have to consider minus cos axis, not cos.
In fourth quadrant now.
Correct. Is it clear, Akash?
Yes, ma'am. Yes, sir.
So it will come in fourth quadrant. It will lead minus cos by 60 degree. Similarly, minus 4 sin omega t plus 30 will come in
third quadrant, ma'am.
Yeah, it will lead minus sin by 30 degree. So what is the angle between these both? This voltage and this current?
120 degrees.
120 degrees.
Correct. So that component power will be 8 into 4 by 2 cosine of 120 degree. This is how you solve such kind of problems. Is it clear?
Hello. Wait, ma'am. If like you have written two frequency 377 and 374.
Yes.
So in this case we have calculated average power.
Yes.
And in this same problem, if I want to calculate reactive power or apparent power, is there any sense of that?
Reactive power and apparent power. For apparent power, it is just VRMS times IRMS.
Okay, तो फिर and react. Okay,
Yeah.
reactive power means okay by these two we can get reactive power.
Correct.
And if like in average power, if 377 frequency and 377 frequency in voltage, so we will get average power. But in reactive is the same. If voltage have 377 and I have 377, so we can get reactive power, or 377 with 374 also we can get reactive power.
With different frequencies also you will get reactive power.
Okay.
How you can solve it yourself? Basic definition of active and reactive powers. If you have a voltage and current, what is the active power? It is the average of product of voltage and current, correct?
Yes.
Okay. Now, if you have voltage, frequency components F1, F2, so on, and current also F1, F2, F3, so on. So you multiply both. So say V is sine omega 1t, I has sine omega 1t, sine omega 2t, so on. Consider the simple case where your voltage has only fundamental, but your current has fundamental plus harmonics. Okay. Now in this case, not clear what I meant?
Clear, ma'am, I understood.
Yeah. So if you find the product of sine omega 1t and sine omega 1t, this is a first component. Next component is sine omega 1t, sine omega 2t. Okay. Third component is sine omega 1t, sine omega 3t. Where my sine omega 1 is of voltage. My voltage has only fundamental. I am taking the simple case. But my current has omega 1, omega 2, so on. We are trying to prove that only similar frequencies constitute active power. Is our aim clear what we are trying to prove?
Yes, ma'am.
Yes.
Okay. So if you multiply similar frequency components, this is sine square omega 1t. What is sine square omega 1t? It is 1 minus cos 2 omega t by 2. Is it clear?
Yes, sir. Yes, ma'am.
Yeah. Similarly, product of sin A sin B. It is some sin A sin B, I don't remember, it will be some cosine of A plus B by 2 plus something, or plus or minus cosine of A minus B by 2. The point is, only this DC 1 by 2 component comes in product of similar frequencies. When product of dissimilar frequencies comes, there will not be any DC component created. All will be sinusoidal components only. Now you know that in one time period, when you integrate a sinusoidal component, the average value will be
0.
0. So for dissimilar frequency components, their average values will come out to be 0. But reactive component, we are not finding average. Actually, when you go deep into it, your P is always your average active power. But your Q is not average reactive power. Average reactive power of a system will always be 0. Whatever you write P plus JQ, P is your average active power, but Q is your peak reactive power. While finding Q, you will never do average function. So in Q, all other multiplication of frequency components will come in your reactive power equation. But in average active power, different frequency products will not come, because when it comes, their average values are 0. Instantaneously, there will be active power. But when you find the average active power, all those terms will turn out to be 0. Only product of similar frequency components will have a DC component. In this also, you know that cos 2 omega t, when you integrate, find average, it will be 0. Only 1 by 2 will have an average component. That is why in such kind of problems, or in generally, product of similar frequencies will constitute your average active power. Generally, in such questions, there is no direct way of finding your peak reactive. Hello? Hello? Chandra, you are not muted. Okay.
Yes, ma'am, please continue. Please.
Yeah. So in such questions, if you are asked to find a reactive power, it is easy to find average power. If you in this quadrant concept, if you learn it quickly, you can find your average power. And apparent power you can find by VRMS times IRMS, where VRMS you know how to find when dissimilar frequencies are there. Say if 180 sin 374t comes, what is your VRMS? It will be root of 170 by root 2 square plus 180 by root 2 square. So you find VRMS. Similar approach, you will find IRMS. You find the product, VRMS into IRMS. Then you already know S square is P square plus Q square. So you find Q as S square minus P square. This is how you find Q, where you should understand that your Q is always the peak reactive power, not average reactive power, but P is your average reactive power. If you are more deep interested in knowing different powers, instantaneous power, average values, you can refer to Stevenson textbook on power systems. Okay, for gate point of view, only this knowledge is enough. Can we move to next question?
Yes, ma'am.
So this is a DC machine problem. All of you are in which year of your BTech or already passed out or?
Yeah, ma'am, I am passed out in 2015.
Any first year, sir? Okay. So the problems I chose for today's session are pretty simple because I wanted to know whether first years or second years are there. And subsequent classes we can increase the difficulty level. Okay. So a 220 volt DC shunt motor takes 3 ampere at no load. It draws 25 ampere when running at full load at 1500 rpm. The armature and shunt resistances are 0.5 ohms and 220 ohms respectively. The no load speed in rpm, round off to 2 decimal places is. So we are given a DC shunt motor. Shunt motor means there will be a shunt branch. Field is shunt. So this is the circuit where this is applied voltage V. This is a field resistance given as 220 ohms. Armature resistance is 0.5 ohms. Back EMF is EB. Now for DC machine, there are two relations which holds true for every DC machines. That is, one is back EMF will be K5 times angular speed in omega, and torque, developed torque by the motor will be K5 times I. The reason I wrote omega is because I can use same K5 in both EB and torque relations. You can also write EB as some K5 dash times N, speed in RPM. Omega is speed in radian per second or angular speed. So these two relations holds true for all DC machines. So in the given problem, we are asked to find the no load speed. So at no load condition, we are given that the motor takes 3 ampere. So it will draw 3 ampere. Applied voltage is already given as 220. So this became a simple networks problem. 220 volt applied across 220 ohms. So 1 ampere will flow in this direction. So 3 ampere we applied. You apply KCL at this node, you know that 2 ampere will flow in the armature circuit. You apply KVL. So 220 volts is equal to EB plus 0.5 times 2, where EB comes out to be 219 volts. So now you know that EB, this is a case of no load. I'm denoting it as case 1. So EB1 is equal to K5 times omega 1. Now this K5 corresponds to the field in the machine. So we are not changing the field. Every time we are applying 220 volts across 220 ohms. So 1 ampere flows through the field winding. So we are not touching the field. So K5 is constant throughout the operation. So this omega 1 is what we have to find. We don't know K5. So we are given another case under full load. It is given that it draws 25 ampere when running at full load. So in the same circuit, now it draws 25 ampere. Now the current through field, what will be the current through the field?
1 ampere, same ma'am.
Same. So the armature circuit current is 24 amps. So now your EB2 will be same 220 minus 0.5 times 24. So it will come out to be 220 minus 12, which is 208 volts. So now you know that this EB2 is equal to K5 times omega 2, where omega 2 is already given, or N. Can someone inform him? Do anyone know him? Because the session is being recorded. That's right.
Yes, ma'am, he's muted again.
Okay. So N2 is given as 1500 RPM. So from these two equations, you get EB2 is proportional to N1 and EB1 is proportional to N1 and EB2 is proportional to N2. So you just have to find the ratio EB1 by EB2, which is N1 by N2. Where EB1 you already know 219, EB2 is 208, and your N2 is 1500 RPM. So your no load speed will come out to be 219 by 208 times 1500, which is 1579.32. So in the problem, it is given round off to 2 decimal places. So this is the answer, RPM. Is it clear?
Yes ma'am.
This is the last question of today's discussion. A single phase transformer of rating 25 kVA supplies a 12 kilowatt load at power factor of 0.6 lagging. The additional load at unity power factor in kilowatts, round off to 2 decimal places, that may be added before this transformer exceeds its rated kVA is. You guys go through the question peacefully and tell me what you understood from this question. Everyone went through the question?
Yeah, ma'am, the transformer have a inductive load, which is approximate half of its load capacity. I'm just rounding off. Now, how much we can add a resistive load so that it must not go beyond its rated value.
Correct. So now, the load power is 12 kilowatt is already given. We don't know what is the reactive power of load. The rating of your single phase transformer is 25 kVA. The load power factor is also given 0.6. Okay. So you know that the transformer is not fully loaded when this load is applied. How you know that? Because 25 times 0.6 is greater than 12. So your transformer is loaded less than its maximum capacity in this question. So how much more load you can add so that the transformer is completely loaded is the question. So we can draw the power triangle where this is your active power, this is your reactive power. The same I explained before applies to here also. This is average active power, this is peak reactive power, and this is your apparent power. And power factor angle is this. You are already given load PL, QL, and this is SL. You are asked to find how much additional PL. It is already given unity power factor load is added. So the new added load will not take any reactive power. It will take only active power. It is a UPF load. So how much, say, X load I can add so that the reactive power is same QL, but your total power now became 25 kVA. This is the question. Understood? So when a new load is added, your power triangle will be P plus X, PL plus X, this is QL, this is 25. You don't know the new power factor. So X is asked. Is it clear for everyone?
Yes, ma'am. It's clear.
Now, Kirti?
Yes, ma'am.
Okay. So now we can use the parameters given in the problem. The load power factor is given 0.6. So phi is cos inverse of 0.6. So what will be QL? QL will be, you find tan in the first triangle, tan phi. Tan phi is QL by PL. So your QL is PL times tan phi. So PL is already given 12 kilowatt, tan of cos inverse 0.6. This will come out to be 16 kilovolt ampere reactive. So in the new power triangle, your PL is 12 plus X the whole square, P square plus QL square, which is 16 square is 25 square. We just have to solve for X. It will come out to be 7.20. It is asked to round off to 2 decimal places. So 7.20 kilowatt. This is the answer. Is it clear?
Yes, ma'am.
Yes, ma'am.
Okay. So that's the end of the today's session. We'll meet on next Thursday.